In the last video, we found that when a line is inclined to both planes, neither view shows its true length. Both are foreshortened. So a natural question remains, how do we recover the real length? That is the whole subject of this video. We will learn two classic methods, rotation and the trapezoid method, and along the way read off the true inclinations of the line as well. First, the intuition. Here are the two planes of first angle projection, forming the first quadrant, and a line placed inside it, inclined to both. This is the real line in space. Its real length is what we are after. When we drop it onto each plane, we flatten out one direction of its tilt. The front view loses the depth. The top view loses the height. Each view is like a shadow, and a tilted stick always casts a shorter shadow than itself. So each method that follows does the same thing. It puts back the one piece of tilt that a view threw away and reads off the true length from the result. In a real problem, you're handed only the two views, the front view and the top view, of a line inclined to both planes. Let us draw them. Here is the reference line, and the front view, A', B' above it. And here is the top view, AB, below it, with the two ends on their shared vertical projectors. Neither of these is the true length. If you simply measure the front view or the top view with your scale, you would get the wrong answer. We need a construction. The first method is rotation. The idea, swing one view until it is parallel to the reference line, because a view parallel to a plane tells the truth. Take the top view AB and rotate it about the end until it lies flat parallel to the reference line. Its length does not change during rotation. Call the new position a B1. Now carry that rotated end up with a vertical projector to the same height as B' in the front view. Join A' to this new point. That join is the true length of the line. By rotating away the planned tilt, the remaining triangle stands upright, and its slope is real. And the angle this true length makes with the reference line is theta, the true inclination of the line to the horizontal plane. Here it comes out to about 31 degrees, with a true length of 68 millimeters. By perfect symmetry, if we instead rotate the front view flat and carry it down into the top view, we recover the true length again. And this time the angle we read is phi, the true inclination to the vertical plane. Rotate the front view about A' until it is horizontal. Carry the rotated end down to the depth of B in the top view and join to A. Again, that join is the true length. The angle here is phi, the true inclination to the vertical plane, about 26 degrees. The two rotations are simply mirror images of each other. The second method is quicker for finding just the true length. It works directly on the top view, using the heights of the two ends. Start with just the top view of the line, AB. At each end, erect a perpendicular to the plan line. Make its length equal to that end's height above the horizontal plane, 20 at A, 55 at B. Now, join the tops of the two perpendiculars. This closing line, the long side of the trapezoid, is the true length of the line. Why does it work? The perpendiculars restore the exact heights the top view had flattened away, so the closing edge is the genuine slant length, 68 millimeters, matching the rotation method exactly. Let's put it all together on one problem. Line AB. End A is 20 above the horizontal plane and 30 in front of the vertical plane. End B is 55 above and 60 in front. Their projectors are 50 apart. Find the true length in both inclinations. Rotate the top view flat, project up, and join. That gives the true length and the angle theta to the horizontal plane. Repeating the rotation on the front view gives phi. Our answers: true length 68 millimeters, inclination to the horizontal plane about 31 degrees, and to the vertical plane about 26 degrees. The third method: instead of moving the line, we move the observer. We hang new projection planes parallel to the line and look through them. And both constructions live on the original drawing itself. Here is the full drawing, front view above top view below, at a reduced scale, so the whole construction fits on one sheet. Every proportion stays true. First construction, draw x1, y1 parallel to the top view itself, at any convenient distance below it. That is an auxiliary plane parallel to the line, seen edge on. Project A and B square across it, and transfer each end's height, measured in the front view right here, beyond the new line. 20 for A, 55 for B. Join the new points. A 1' B1' is the true length, and the angle it makes with x1, y1 is theta, the true inclination to the horizontal plane. 31 degrees. Second construction, same idea, other view. x2, y2, parallel to the front view, drawn above it. Project a prime and B' across, and this time carry the depths from the top view, 30 and 60. Join. The true length again, 68 millimeters in perfect agreement. And its angle with x2, y2 is phi, 26 degrees. One drawing, two fold lines. Transfer heights to find theta. Transfer depths to find phi. This is the auxiliary plane method, exactly as you will draw it on your sheet. One step further, because the auxiliary plane idea does not stop at true length. This time we will run the complete construction, start to finish, on a single figure. Step 1. The given views of the same line as before, front view above the XY line, top view below. Step 2. The method we just learned. X1, Y1 parallel to the top view, heights 20 and 55 carried across as arrows from the new axis, and there is the true length. Step 3. A second auxiliary plane, X2, Y2, drawn perpendicular to the true length, perpendicular to the line itself. Looking through this plane means looking straight down the barrel of the line. Now the beautiful part. Because X1, Y1 was drawn parallel to AB, both ends of the top view sit at exactly the same distance d from it. Equal arrows, that is the whole secret. Step 4. Project along the line across X2, Y2, and carry that same distance d beyond it. Once for A, once for B. Both land on the same spot. The whole line has collapsed to a single point, a 2, identical with B2. And why care? Because in the view where a line is a point, every distance to that line shows true size. The shortest distance from any point to the line, from a pipe to a cable, from a strut to an axis, becomes one direct measurement. Let's recap. You now have everything for lines, how to project them, and how to recover their true length and true angles when they tilt in space. In the next sheet, we move from lines to plane figures, projecting triangles, squares, and circles. Practice this example with your own numbers before then. See you in the next one.